Let's continue to work towards a general proof for the algebraic properties of matrix column vector multiplication. In this case, we'll work towards the scalar multiplication form of that, which reads, if we have an m by n matrix and I suppose one vector x in Rn by 1 and one scalar alpha that's just a real number, then we have that a times alpha times x must be equal to alpha times a times x. In other words, I can pull the scalar outside the multiplication. Remember from our last video, when we're trying to transform a theorem into a logical structure that allows us to do direct proof, we often want to identify a conditional statement. So state the theorem using the P implies Q format. We called P the antecedent and Q the consequent. And the way we read this in English was if P, then Q. Let's explicitly state the antecedent. So if P, we'll go ahead and write the antecedent out. If A is a m by n matrix, X is an n by 1 vector, and alpha is a single scalar, then Q, then it must be the case that A times alpha times X is equal to alpha times A times X. Just like we did before, we're going to use the key problem-solving questions to get deep insights into what we're trying to do as we devise a plan for the proof that we're looking for. In this case, we'll focus on understanding the problem. Let's separate the consequent Q into various sub-pieces or sub-parts and analyze each one individually. To that end, when we assume P to be true and we want to show Q, what we really want to do is show that expression 1 is equal to expression 2. Just like we did before, we're looking for a general proof, but sometimes that's elusive, especially if we're not fully clear on what the operations are. So what we'll do is, let's go ahead and just create some examples in a base case scenario. We'll get intuition in the simpler case to hopefully guide our proof in the general case. That comes from our problem-solving questions. Is it possible to simplify the problem to a related accessible problem and then generalize our intuition from that? So in this case, we'll say that m is 5 and n is 3. One of the major questions is, how can I get a big enough problem to be interesting, but small enough to be manageable? Now that we've thought about what expression 1 looks like, let's analyze expression 2. Notice in this situation, I have an m by n matrix and an n by 1 vector. So that's matrix column vector multiplication. Over here, this is scalar vector multiplication. This scalar vector happens in n by 1 space. This scalar vector multiplication happens in m by 1 space. Different sized vectors, but same operation underneath. The whole time I'm looking at this, I'm also thinking about my problem solving questions. Do I know any theorems or definitions that might be useful? Why, yes, indeed I do. I know what the definition of scalar vector multiplication is, and I also know what two different definitions for matrix column vector multiplication. For those of you that are watching at home, if you don't have those off the top of your head, this would be a great time to review it. Do active recall. Test yourself, verify your test, and then correct any mistakes. That's how you strengthen your brain, by repeatedly trying hard, making mistakes, and then correcting. Notice that one of the key things that we're trying to do in this proof is show that the vector on the left-hand side, a times alpha times x, is equal to the vector on the right-hand side, alpha times a times x. I asked myself, do I know anything relevant that might help me on that? And I actually do. I remember that two vectors are equal if and only if each individual entry of those vectors are equal. So another alternative version of this proof might be, can I show that each entry on the vector on the left is identical to the individual entries on the vector on the right? The moment that I have that written, I might also remember that when I'm looking at the entries, these have to align for all of them. I'm thinking in this case, m is going to be equal to 5, but in the general situation, it just goes up to any general integer m. Moreover, the key operation is a matrix vector multiplication, and I actually have a definition that gives me the entry by entry version of how to calculate that. It's called matrix column vector multiplication via dot products. So with that in mind, let's go ahead and set m equal to 5 and n equal to 3, and we'll look at a concrete example. Let's have a be an element of R 5 by 3, x element of R 3 by 1, and alpha a scalar. And we remember what we're trying to do is show that the ith entry of the expression on the left, a times alpha times x, is equal to the ith entry on the expression on the right, which is alpha times a times x. Let's start with entry I of a times alpha times x. We remember from the dot product definition, let's think for a minute. If I want to find the ith entry, what I'm going to do is take the ith row of my matrix, turn it into a column vector via transpose, and then dot it with my vector x. So in this situation, I'm going to take the ith row of the matrix A, that's this thing, right? This is colon notation with the transpose. I'm going to do a dot product with the vector that I'm multiplying by. In this case, the vector is alpha times x. Here we've assumed A is going to be a 5 by 3. So the ith row is going to be a 1 by 3, which means the ith row transpose is going to be a 3 by 1. Let's think about that. The ith row is going to be AI1, AI2, AI3. When I transpose, it's going to be AI1, AI2, AI3. Here, the vector x is going to be x1, x2, x3. When I multiply by alpha, I bring those inside. So this is going to be alpha x1, alpha x2, alpha x3. To get that ith entry, I take the dot product, which means I just multiply each of those individually. So this is AI1 times alpha x1 plus AI2 times alpha x2 plus AI3 times alpha x3. Well, check that out. The scalar alpha shows up in all three parts, which means I can pull it out because this is scalar addition. This is literally factoring out or reverse distributivity of scalar multiplication over scalar addition. So now I have alpha times AI1 x1 plus AI2 x2 plus AI3 x3. In that situation, we see this as the ith row of A dot product with x, so that's the opposite direction, but that is exactly the entire ith row transpose dotted with x. That's exactly the entry I of alpha times A times x. That's what I wanted to show. In this case, we did only in the forward direction. I kind of sped it up a little bit. In order to do this fast, I have to be really fluent with my definitions. My claim is this exercise is not about going fast. This exercise is about solidifying the definitions in your mind and using base cases. Community challenge for you all. How could you generalize to the m by n case? So how could you use this in the m by n case? Another community challenge. What if you wanted to use a proof based on the matrix column vector multiplication via linear combination? So instead of proving the entry by entry situation, what if you wanted to prove the entire vectors are equal using linear combinations in the way we've seen it? Can you generate that proof? Thank you so much for your attention, y'all. Let's keep going deeper in matrix column vector multiplication. I'll see you in the next video.